Welcome, everyone. In today's session, we'll focus on the process of training a machine learning model using a training dataset. This is one of the most important steps in the machine learning workflow, where the model learns patterns and relationships from data to make accurate predictions. For today, we will frame our discussion within the context of public policy. By using real-world examples, such as predicting voter turnout or identifying regions in need of infrastructure improvements, you'll see how machine learning can support evidence-based policymaking. By the end of this lesson, you'll understand how training works, the best practices to follow, and the challenges we often encounter in this process. Training begins with defining the problem you want to solve. In public policy, this could be predicting voter turnout in a given region for an upcoming election. This is a classification problem, where the goal is to categorize areas as having high or low turnout. Another example is predicting the economic impact of new public infrastructure, which is a regression problem since the goal is to predict a continuous variable like GDP growth. Once the problem type is clear, the next step is selecting an algorithm. For classification problems like voter turnout prediction, logistic regression or decision trees might be appropriate. These algorithms allow us to analyze patterns in historical data, such as previous election turnout rates, demographics, and campaign efforts. For regression problems like forecasting the economic impact of infrastructure, linear regression is a common choice, as it helps model relationships between variables like investment size, regional GDP, and employment rates. Next, we prepare the dataset by splitting it into training and test sets. The training set, typically 70 to 80% of the data, is used to teach the model patterns and relationships. For example, in our voter turnout prediction problem, the training set might include historical data on voter demographics, weather conditions on election days, and the number of polling stations. The test set, which makes up the remaining 20 to 30%, is reserved to evaluate the model's performance after training. The training process itself begins by feeding the training dataset into the selected algorithm. Using tools like scikit-learn or TensorFlow, we use methods such as .fit to train the model. During training, the algorithm adjusts its internal parameters based on the patterns it observes in the training data. For instance, in the voter turnout example, the model might learn that regions with younger populations and more polling stations tend to have higher turnout. Similarly, in the economic impact prediction problem, the model might learn that infrastructure investments in transportation have a stronger effect on regional GDP than investments in other areas. To train models effectively, we need to follow certain best practices. First, we monitor the training loss, which measures the error between the model's predictions and the actual values in the training dataset. For example, in the voter turnout case, if the model predicts low turnout but the actual data shows high turnout, this contributes to the loss. The goal is to minimize this loss so the model learns patterns accurately. However, we need to be cautious about overfitting, which occurs when the model performs exceptionally well on the training data but poorly on new, unseen data. For example, if the voter turnout model memorizes specific data points from past elections, it may fail to generalize to future elections with different conditions. To address overfitting, we can use regularization techniques that penalize overly complex models or simplify the model by removing less important features, such as minor variations in voter age groups. Another important factor is the learning rate, which controls how quickly the model updates its parameters during training. If the learning rate is too high, the model might miss critical patterns, such as the interaction between demographic factors and weather conditions. Conversely, if the learning rate is too low, the model might take too long to converge. A balanced learning rate ensures the model learns efficiently without skipping over important details. Training models in public policy settings often comes with unique challenges. One major issue is insufficient data. For example, if a city has only conducted a few public surveys about voter turnout, the dataset may not be large enough to capture meaningful patterns. In such cases, data augmentation can help. For instance, we could combine survey data with other datasets, such as census information or past election results, to increase the dataset size and diversity. Class imbalance is another challenge. In public policy, this often happens when predicting rare events, such as identifying areas at risk of severe natural disasters. For example, if only a small number of regions experience such events, the model may struggle to learn patterns for those cases and instead focus on the majority class. Techniques like oversampling the minority class by generating synthetic data for at-risk regions or undersampling the majority class can help address this imbalance. Noisy data is also a common obstacle. For instance, datasets in public policy may include errors, such as incorrect demographic information or outdated infrastructure records. These inaccuracies can confuse the model during training. Pre-processing the data by removing outliers, standardizing formats, and ensuring data accuracy is essential to improving the model's ability to learn effectively. To summarize, training a machine learning model involves defining the problem, selecting an appropriate algorithm, preparing the dataset, and teaching the model patterns using methods like .fit. In public policy settings, training might involve predicting voter turnout, analyzing economic impacts, or identifying at-risk regions. Best practices, such as monitoring training loss, avoiding overfitting, and carefully managing the learning rate, are crucial for effective training. At the same time, addressing challenges like insufficient data, class imbalance, and noisy data ensures the model learns robustly. Training is just the beginning of the machine learning journey. In our next lesson, we'll explore the validation stage, where we evaluate how well the trained model performs on unseen data. Validation ensures the model can generalize to real-world scenarios, making it a vital step in the machine learning workflow. Thank you for your attention, and I look forward to discussing validation with you in our next session.